So now that we have analyzed the binary a bit, right, we have managed to isolate some of the functions that it's been calling. So these are the functions that the attacker, the commands that they're sending down to our computer, and then the functions that are getting run when they receive those commands. But remember, now that we have determined how those commands are being parsed and how those commands are being handled, we still haven't actually seen what commands are being sent. So this is where we bring in a bit of network analysis, right? This is why I taught you all how to use Wireshark before we started looking at this, okay? Hello, Vu. Okay, what I want you guys to do is inside this folder, there is a pcat file called C2 traffic. This is a network log that was captured on the infected computer. You can double click and give it an open. And you can see that there is no nice protocol that is defined here. It's not it's not HTTP, it's not FTP, it's not SSH, nothing, right? This is raw TCP. Everyone can see this? Okay, so first and foremost, I want you guys to try and make an independent observation, an observation that doesn't require you to look at the code at all, just looking at the traffic. So firstly, when going through, you can see JSON, right? You can see the JSON text that's being sent from the client, which is the victim computer, and the attacker. So we can see operation key exchange, and then something called nonce. Then we can see operation key exchange, acknowledge, and then another nonce value. And then afterwards, we just see a whole bunch of other packets, right? So what I want you guys to do to make our lives a bit easier, go to packet number 4, right? Packet number 4. And I want you guys to click on data. When you click on data, it should highlight. Click on, okay. Don't right click. Down here, bottom left, click on data. Like, don't expand it. Expanding it is like clicking the small left, right? I just want you to click on it so it's highlighted. Okay, the reason why I'm asking you to do this, right, is because when you click on this and it's highlighted, on the right-hand side, the data becomes highlighted. Do you all see this? For you guys, it should be blue, I think. So since it's highlighted, now when we start stepping through other packets, right, every time we have a data section, that data section will be highlighted for us. So you guys just do this and see if it holds up for you. So the data section should get highlighted on each of these. Okay, the next thing that I want you guys to acknowledge, right? Just acknowledge first as a truth. Over here, we have key exchange. And here we have key exchange ack or acknowledge. What concept did we cover earlier that might correspond to this? Handshakes, correct. We are starting off our communications with a handshake between the victim and the attacker, right? So there is a handshake that is taking place. And what is the implication of a handshake? Yes, that the subsequent communications between the attacker and the victim will be encrypted. And this aligns with what we saw earlier in the binary. What we saw earlier was that AES is being used, right? And if AES is being used, that means there's some form of encryption that's being used, correct? And if encryption is being used, then that means that our packets are probably encrypted. So something else that I want you guys to observe, right? Inside all of these packets, even though the subsequent ones are encrypted, there are a few bytes that are still the same, that are consistent for every single packet. I want you guys to just stare really hard at the highlighted sections, and I want you to point out what it could be. Very good. Observe very fast, right? I want you guys to notice that in the data section of all these packets that should be highlighted for you guys, the first 4 characters are always SHKL. 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 What concept does this map to things that we have seen before? Magic bytes. Very good. So this actually helps us to answer question number 16. What magic value do all these transmitted packets start with? What's the magic? SHKL. SHKL, right? And the hex value for SHKL, I'm just gonna take this down as a note. SHKL is 5348 4B and 4C. Okay. Let's just take this down. Let's keep this in mind. Right? So SHKL, that's our magic. We can see this. Okay, you guys don't have to strictly follow along for this portion because I will zip through the binary a bit fast for this. But since we know that SHKL must exist somewhere in the binary for us to send and receive, right? We can actually observe this ourselves. For example, right, when we are sending frames, notice that when we send a frame and then we send it, we have these bytes here. Anything suspicious looking about these bytes? They're the same. This is the SHKL bytes that we are copying into the packet that we're sending to the attacker, right? So SHKL exists inside our binary. Better yet, when we receive a packet from the attacker, so it should be in receive frame, right? It checks the first 4 bytes of the frame, and it checks if it equals to 53484B4C, and that is SHKL. So this is a form of packet validation, right? When it sends packets to the attacker, they must start with SHKL. When I receive packets from the attacker, they must also start with SHKL. All clear? Okay, so that's the first part. There is a script that you guys need to edit along the way, actually. So if you go over to the shark loader folder and then pass pcap, you should see at the start it's requesting for a magic. So can everyone get to this this script? Everyone should be able to find pass pcap.py inside the same folder as the C2 traffic and the sample. Okay, so does everyone have this open? Okay, what we're going to fill in for the magic here is going to be a bit awkward syntax-wise because I wrote the script pretty badly. But what we're going to fill in is the magic will be int.form bytes. And then what's the magic that we've determined? SHKL. So what this function does is it will convert the bytes SHKL into the integer, which is the hex number 0x53484B4C, right? So int from bytes SHKL. I want everyone to fill this in for the magic, right? Because that's the magic that we've isolated, that we have independently discovered by staring really hard at the network space. You all shouldn't be able to run the script yet. I just need you all to fill in the magic, right? So far so good. We've isolated the magic. Let's see what else we're gonna look at, right? Ooh, okay. So, yes, handshakes. So I brought up handshakes earlier with our double lock box. And to just repeat one more time to really drill in the concept. To establish encrypted communications, right, we first have to do a handshake where the client and the server will agree on how they want to communicate. So in this case, we have a handshake 2, right? Our handshake is by first sending what's called a nonce value. Anyone know what a nonce is? Number used once. So it is a unique number that is used one time for communication. So the client, the victim, sends its own nonce value to the server. Then the server will send back a nonce value in a response, right? Can we see what the nonce value is here inside the packets? Yes, right? What encoding is it using? Base 64. So knowing that it's a base 64 encoded nonce, we can once again isolate this ourselves and put it in our own code. So give me a moment so I can double check the format for this. I want to make sure the formatting is correct. So what we're going to do is we're going to base 64 decode the nonce ourselves. Okay. So we know that the exchange is being done with a nonce. So if we go to pass pcap and then we scroll down, we can see it expects to see a client nonce and a server nonce. Yes? Okay. So what is the client nonce? Can just read out the first few characters of it. DYA, so on and so forth, right? And before we start filling anything in, I want you guys to observe inside the code where this comes from, right? And we'll do a bit of renaming along the way. This is more show and tell if you manage to like keep up like good, but like it's okay if you don't do all this renaming also. You can see we start our code here. So after we establish connection to the C2, this is, remember earlier when we calculated the host name, right? We decrypted the host name. After decrypting the host name, we establish a connection to it. So that we're mapping out the logic of the malware now, right? We establish a connection to the C2. After establishing a connection to the C2, we then follow up by opening dev urandom. Anyone want to take a guess what dev urandom is? Random bytes. This is a random number generator that's built into Linux. So we have an RNG here. Then we start reading from the RNG. We read into local 198, and we read 16 bytes into it. Local 198 is later base 64 encoded. And judging by our understanding, what we saw inside the packet, right? What was that base 64 encoded value? What was it? Like, what was it called? Inside the handshake. Nonce, right? The base 64 value is a nonce. So that means that this RNG value that we're reading is likely the nonce, right? Furthermore, base 64 encode, the output of base 64 encode would be the base 64 encoded version of the nonce. And you can see all of this is lining up so far, right? Nonce is a number used only once. How do you get a number to use only one time? You randomly generate the number lah, right? If you want a secure number that's only used once, you should randomly generate the number. So we get a nonce value from our RNG. We base 64 encode it to get the base 64 encoded nonce. Then you can see this is the structure of the packet. The exact structure of the packet that we see in Wireshark. So op key exchange nonce and then the base 64 nonce. Op key exchange nonce, then the base 64 nonce. So this is our handshake client hello, right? This is our client hello. And then we send the client hello over the line, over our socket. So this is what's happening here, right? This block of code corresponds directly with this packet being sent over the wire. Can we all see this? Do we all understand so far? Okay, anyone lost? Anyone like really lost? I'm not getting you all to type anything right now. Like I just need to see whether you guys sort of get it, right? I will repeat one more time. Our malware opens a random number generator and uses it to generate a 16-byte nonce, which is a number used only once. It subsequently base 64 encodes this nonce. Then it sends it to the attacker, and it sends it in the key exchange JSON format, right? Which corresponds directly here. Key exchange in a JSON format, and a nonce value that's base 64 encoded. So if we want to extract this nonce value, we would have to take this base 64 value and then decode it. Agreed? So we can go back to our Python script. What we're going to do is we're going to base 64 dot b64 decode. So this is to perform base 64 decoding in Python. And we will decode this base 64 string. So if you want to copy out data from Wireshark, right click, and then in this case we need to copy it as ASCII. So I will do again. Highlighted data, right click, copy as ASCII text. Then inside Python, right, you can paste it in. You see it's got like the base 64 string here. We're just gonna copy that part only. And then we put it into our base 64 decode. Then I'm just gonna delete all the other nonsense because it's not relevant. So afterwards, you guys should see our client nonce is base 64.b64 decode of the base64 string that we got from this packet. Now that we know how it looks like for the client sending, right? We expect the handshake to have a similar format for the server response. So in this case, very obviously, what is the server nonce without the first few characters? SL, E, so on and so forth. So we'll do the exact same thing. We are going to copy this as ASCII text, and we're going to take out the base64 string and the base64 string only. I'll just put it one side first. And then we'll do base64 decode. So it should look a bit like this at the end. So everyone should get a script that should look like this in its current state. Yes? Good? Okay. So this actually lets us answer question 17a, right? Those are the nonce values that are being sent. Now, what is important is knowing what is being done with these nonces, right? So congrats, we now have the nonce from the client side and the nonce from the server side. But do we know how they actually use these values to derive the key? No, we don't know that yet, right? So now I want you guys to try and follow along, right? I'm going to explain how the nonce values are being used to generate the key. So I want you guys to look at the following, right? So over here, these first few lines that we were looking at, this is the client side. So this is the victim, the infected computer, generating its nonce and then sending it to the server, correct? Afterwards, down here, this is the receive side. So this is when it receives the nonce from the server. So you see it's in reverse. Just now we did generate number, base64 encode, then send. Now we're doing receive, JSON lookup, and then decode. Can follow along? Okay, so we receive a frame, we decrypt the frame, we look up the nonce value from the frame. So this is the server nonce B64. And then it's decoded into this variable local 188, which is our server nonce. And then I want you guys to see how the nonce values are being used. So we have the nonce value from the client, and we have the nonce value from the server, right? And we are both passing it into this function called SHA-512. Let's jog your memory. What SHA-512, what type of algorithm is it? Hashing algorithm, right? So it can take in some input, and it will generate some unique output based on the input. I want you guys to know how this is being used, right? The client provided nonce A. The server provided nonce B, right? Now, if the client has nonce A and nonce B, and they put them together and they hash it, they will get some value, correct? Now the server does the same thing. It has nonce A and it has nonce B. They can put it together, hash it, and it will produce the same thing. So that means that now they can generate a shared key to use for encryption. Make sense? Make sense? Okay. So this is how the shared key is being generated. They are taking the nonce and the server nonce, smoosh together, then hash it. And this is reflected in the Python script that I've given to you all. Notice how after we have decoded the client nonce and the server nonce, we take the client nonce and the server nonce, we smoosh it, then we SHA-512 to get out a hash value. So you just add it together. You concatenate them. Because the output of base64 decode is bytes. So it's a byte sequence and a byte sequence, kiss, then hash. So now this is a common value that both the server and the client will have, right? And with a common value, then they can start using symmetric encryption, which is AES in this case. But AES, how do we go from the hash and then turn it into the AES key, right? So let's go back to our decomp. Our output from SHA-512 goes into local 158. So this is the hash result. And then you just look at this really long section. You see, AES key 0 equals hash 0, AES key 1 equals hash 1, so on and so forth, so on and so forth, right? So the first character of the AES key is the first character of the hash. First, the next character of the AES key is the next character of the hash, so on and so forth. How long is the key? Well, the answer is 32. Remember, it's 0 index. So if we are indexing up to 0x1f, 0 to 0x1f, 0 to 31 is how many numbers? 32 numbers, correct. And this is consistent with our understanding of AES, right? AES keys are either 16 bytes long or 32 bytes long. In this case, it's 32 bytes long. So that means that the first 32 bytes of our hash output is our key. And we can actually do this in Python, right? The first 32 bytes, 0 to 32, of our hash is our key. That is consistent with the logic that we have analyzed. Okay, then AES requires another thing called an IV, right? And I want to turn this into a learning point, right? Over here, the AES IV is determined to be 8 bytes long because this is what Ghidra has assumed it to be. But this is because decompilation is not perfect. The problem here is that the AES IV, can someone do a quick Google search, right? If AES key 32 byte long, how long must the IV be? Just quickly Google that. Wrong. 16. The IV for a 32 byte long AES key is usually conventionally 16 bytes long, right? However, Ghidra has made a blind guess and assumed that the AES IV is only 8 bytes long. This is because it split up the assignment of the IV into two operations. Notice how data 1081A8, right, is adjacent to the IV. So 8 bytes here and then 8 bytes here. Actually, this is supposed to be the same variable. This is supposed to be one full 16-byte variable, but Ghidra sliced in half. But we are better, and we know that decompilation is not perfect, so we can make our adjustments accordingly. So based on what we see, this means that the IV is 16 bytes long, and it's the 16 bytes that come after 32, like the first 32. So that means our slice should be the C 32 48, because 48 is 32 plus 16, which is equal to 16 plus 32, right? And with this, we have now figured out how the key exchange between the client and the server is done. We have figured out the magic bytes of the packets to isolate which packets we should be looking at. We have figured out how the AES key and the IV are derived from the handshake. And finally, we should be able to run the script and decrypt the network traffic between the malware, the victim, and the attacker. So if you run pass pcap.py, it'll take a tiny bit to churn, found 16 frames, derive the AES key, and it has decrypted the conversation. And now we can see all of those commands, all of those functions that we were looking at earlier, our fingerprint function, our list directory function, our shell function, right? Now all the communications between the victim and the attacker have been decrypted, and this is the information that got stolen. And at the very end, you can see they listed files, they downloaded the flag. Okay. Yeah, I know I was a bit fast. So, to repeat, for the AES key and IV derivation, right? From where do you need me to start? From the nonces or?
No, just after we get a hash, then how do you get IV?
So, we know that the length of the AES key is 32 bytes long, right? The thing is, the Ghidra output is imperfect because the hash result of SHA-512 is actually 64 bytes long, not 32. So you see there's a mismatch here. This says UCAR32, right? So actually this should get extended if I can retype it, that is. So this is a different command that I didn't show you guys, right? If I control L, you can see this is the data type that it identified it to be, which is unsigned character 32, right? I can change it to unsigned character 64. And it will actually like re-evaluate the decomp. And then you can see now it's changed. AES IV now reflects me taking 32 to 48 from the hash. Yeah. And then same thing, AES IV is actually supposed to be 16 bytes long, but Ghidra thought is only 8 bytes. Now this one is a bit harder to rectify because it treats it as an undefined 8. But if I turn it to UCAR 16, I think that is allowed. No, cannot. You see, it can't do it because it will clash with this other variable. And these two are already defined. So like this tiny bit is a bit too complicated for me to do like on the spot, right? So if I clear this, I think I can clear it like that. Then I can retype it. Should be UCAR 16. Yeah, you see? So if I clear it out, if I clear out the incorrect output from Ghidra and then I retype it to be 16 bytes, then now it's suddenly a lot clearer. See, is this better? Like you see, you can see where the IV comes from now? Yeah. So actually, you know, I'll just repeat that, but like louder so everyone can hear and see, because this is actually quite important and very ooh, my compiler process died. Okay, this is quite important for like more advanced analysis, right? So like I said earlier, the output from Ghidra is imperfect, right? It doesn't always get the sizes or the lengths or whatever correct because it is making assumptions from the assembly. This is a problem that is always faced when working with decompilation. So for example here, local 158 is our hash, right? If you Google how long the output of a hash from SHA-512 is, it will tell you it's 64 bytes. However, if you look at what Ghidra guessed our hash length to be, it guessed it to only be 32 bytes. So you don't have to be forced by Ghidra to accept its mistakes, right? So just now, okay, I guess you guys can follow along if you wanna, right? Just now we would press L to rename a variable, correct? Have you guys all renamed hash? Like just to check. If you haven't renamed hash, just do it now so that you can actually follow along this portion. So like local 188 should be renamed to hash. So you see the hash was incorrectly identified to be 32 bytes long. We're now going to convert it to the correct length, which is 64. So instead of pressing L, just L, we're going to press Control then L. See, when you do Control L, there's a different dialog which tells you the type that Ghidra has identified the thing to be. So in this case, it's identified to be a UCAR unsigned character of 32 bytes long, right? Instead, we'll change 32 to 64. Then you can see the moment I did that, right, these two hanging variables below it suddenly got eaten up. They suddenly got eaten up. That cleans up our decompilation a bit because those two variables were not helping us, right? It was actually making it more confusing. And now, when you look at the assignment of the IV, we don't need to make any assumptions about the IV length or whatever, right? Now, instead of seeing two weird variables that we weren't analyzing at all, we just see our hash, the next 16 bytes of our hash array being accessed. Agree? But then it's still a bit ugly because AES IV was incorrectly identified by Ghidra to only be 8 bytes long. So it assigns the 8 bytes of IV, then it starts to assign it to a different variable. But we know that they're actually the same, combined, right? So if we go to AES IV, like if you double click and it brings you to the disassembly view, what you can do is you can select AES IV and the variable that comes after it together. Right click, oops. You select these two, then when you right click, you can press clear. So clear code bytes. What it does is it tells Ghidra, oi, whatever you analyzed just now and whatever you assumed is wrong. I'm going to clear it out and I'm going to define it again. Then when you go to AES IV, same thing, Control L. Then instead of undefined, I can tell it it's a UCAR 16. And then if you hit that, suddenly our decom is very clean. It now shows that our IV is 16 bytes long and it's reading from 0x20, which is index 32, all the way to 0x24, which is index 47 of our hash. So it's okay if you weren't able to follow along for this portion exactly, right? This is just to illustrate to you guys that decompilation output often imperfect, but can be cleaned up. And with that, we've managed to make it through our big malware sample. So good job, guys. We have managed to analyze a remote access Trojan, and we have managed to decrypt the communications between an attacker and a victim device. That's malware analysis and reverse engineering. Okay, that was very long. I think you guys can take a 10-minute break. And then, since we actually still have time, I will touch on one of the more advanced topics. I'll do the IP example. I'll touch on one of the more advanced topics, and then we'll wrap up the workshop, okay?